Welcome to the Financial Math lesson on interest. This is part one, where I'm going to talk about simple compound and continuous interest and effective rate of interest. And then there'll be a second part where I'll talk about some additional topics. On this slide, I'm going to talk about simple interest. This is the simplest of the different interest arrangements that I'm going to talk about. So simple interest is computed based on the amount of principal and time duration, but without any compounding. Simple interest can be applied to a loan or to money saved in a bank. In the most basic form, simple interest entails an interest rate R, which is typically stated per year, but not always, a given amount of principal P, and a term T, when the principal and interest is paid back to the lender. The term is typically stated in years or fractions thereof. Under these assumptions, the amount of simple interest plus the original principal is given by this formula here. So P is the original amount, and then you have to multiply P times the simple interest rate and the time interval. And you can also factor P out of that and get this formula here that I have in green. So let's look at a particular example. Mr. Smith purchases a car from a car dealer at $28,440. He agrees to make an upfront payment of $20,000, and the car dealer agrees to allow Mr. Smith to pay the remaining amount with 6% annual interest, simple interest, in 7 years. At the end of 7 years, Mr. Smith must pay $8,400. That's the amount that's principal, the amount of the loan, plus the simple interest over 7 years. And we compute that with this part of the formula here. So it will be the principal times the yearly interest rate, and then it's 7 years. And so that comes to $3,528. I have another type of loan that's different from simple interest. It's called the balloon loan, but just in terms of comparison, I'll give you that example here. And then in a future lesson, I'll talk more about balloon loans in a little bit more detail. So let's say that Mr. Smith pays the principal back to the car dealer at the end of 7 years. So that's similar to the simple interest, but he must make monthly interest payments in the amount of $8,400 times the 6% divided by 12, $42 per month. So the accumulated amount of interest paid to the car dealer is an arithmetic progression. We talked about those in the last lesson. So it would be 42 and then 84 total and 126. By the final payment, the total would add up to 3528, which is the same as we have here. And then at that time, all the interest would have already been paid, and then the balloon part of the loan, the principal, would need to be paid back at the end of the period. Now, I know that's not typical for a car loan, but I'm just giving it as an alternate example to a simple interest. I put this example in my book. In fact, it's pretty much what I had in my book, and the one person who reviewed my book on Amazon didn't understand this. He went ahead and did it and confused this with simple interest, and then he condemned my entire book as being bad math based on his misunderstanding. And if that wasn't enough, he said there was no Python. And you already seen that in the first lesson, I had 2 Python programs, and I have several more here. So in the event you're looking to buy the paper copy, I would please disregard what that one person said. It's totally off base. On this slide, I want to talk about compound interest in regard to saving money. There's also an aspect where you're paying a loan back like a mortgage where you have compounding, but I'll talk about that in a future lesson. So compound interest is computed on the sum of the original principal plus accrued interest. Compound interest can be thought of as interest on interest and grows faster than simple interest of the same rate. We have a term here, nominal annual interest rate, or just nominal interest rate is used here as the interest rate as stated without adjustments for the effect of compounding. An interest rate is called nominal if the frequency of compounding, for example monthly or daily, is not identical to the basic time unit in which the nominal rate is quoted, normally a year. So for example, just to clarify this, and you've probably seen this in different ads from a bank, they may advertise a nominal yearly interest rate of 6% compounded daily, and then they'll say something like, which is effectively about 6.183% when daily compounding is applied. So in other words, if you kept it for a year, you would actually make this much interest, even though they're saying it's 6%, because of each day they're taking 1 over 365 times 6%, and that amount of interest, and they're adding it to your money. Then you have a slightly higher principal the second day, and they do the same thing. They take 1 over 365 times 6% again, multiply that times your new principal and add that, and that gives you a slightly higher interest rate over the course of a year. Okay, so that's the advantage of compounding. Have some formulas I'm going to talk about on this slide and the next. Let P be the initial principal. So that's pretty typical for all the different types of interest computations. So for example, the money placed at a bank, let R be the nominal annual interest rate, annual, yearly, in other words, N be the compounding frequency per year, and T be the length of time the interest is applied, using the same units as R, our nominal interest rate. The table on the next slide shows the computation of principal after the first, second, and final compounding intervals. And I'll explain this again when I get to the next slide. The entries in the right-hand column constitute a geometric regression with the initial term P and multiplier 1 plus R over N. It's the annual interest rate divided by N, the number of compounding frequencies per year. Okay, so that's a bit to take in. We'll go through this more formally on the next slide and then some examples. In this table, I calculate the formula for compound interest. You start with the initial principal. Then after the first compounding, you have the initial principal plus the interest rate for just that one compounding period. So it's R divided by N. So in other words, if you had 6% interest and periods per year and compoundings once per month, then you would divide 0.06 by 12 and multiply that times your principal, and that would give you the amount of money you had at the end of the first compounding interval. Then you start with this number, and I factored the P out. You start with this number as your kind of your new principal in the second period, and you multiply that again by R over N. So R over N times this, add it to this amount, and you can factor out a 1 plus R over N, and you get this here. And then I just multiply these together to get this. And if you do it another time for the third interval, you're going to just get P times 1 plus R over N cubed, and so on, until you've hit the final number of compounding intervals, which would be N times T. And so this is our formula for compound interest. And another way of looking at this, and I've kind of hinted at it already, is noted here in this paragraph. If we let I equal the interest rate per compounding period, so that would be R divided by N, and then S be the number of compounding intervals, that would be N times T. And if you plug in I and S into this formula, you get P times 1 plus I to the S, being the accumulated amount of principal after S compounding intervals at a rate per compounding interval of R divided by N. I'll show you an example in the next slide that hopefully makes it a little bit clearer. A couple of other things just in terms of notation, which I'll mention here. It's a notation I'm not going to use, but you may see it if you look in other financial books. They sometimes use this notation I to the N to indicate a nominal annual interest rate that is compounded N times per year. So this is basically our R is I to this N notation here. I don't like this notation. It looks like it's I to some power, but it isn't. It's just an awkward notation in my opinion. Secondly, if the nominal annual interest rate is I, we would say that I to the N equals I for all values of N, which is also confusing. So I've avoided using this notation as much as possible, and we've taken the approach of writing out in prose what is meant in particular. So nominal annual interest rate of 6% compounded monthly, rather than writing this notation here, which kind of means what I've written in words here. Okay, with that said, let's look at an example to help make this a little bit clearer. So let's have our example. You're given a nominal interest rate of 9% per 18 months. I shifted things around. So I know I said it was usually annual, which is the case, but it doesn't have to be. So in this case here, our nominal interest rate is per 18 months, and it's 9%. Which is compounded every 2 months. Again, I kind of made it a little bit different from what's typical. If the initial principal is $1,000, how much money do you have in 24 months? So I'll give you the answer on this slide, but if you want to give it a try, you may want to just pause your video here, give it a try, and I'll come back in a second and I'll show you how to do it. Okay, so I'm back. Here's our solution. So we're given nominal rate 9% per 18 months, but there's compounding every 2 months. The principal is $1,000, and the time interval that we're looking at is 24 months. So we want to know how much is our $1,000 grown over 24 months. So first step, we convert the nominal rate to a rate per compounding period. The nominal rate is 9% over 18 months, and the compounding happens every 2 months. So there are 18 divided by 2, 9 compounding periods over our 18 months. And so we want to divide the interest rate, the nominal interest rate, 0.09 by 9, and we get 0.01. So in other words, you get 1% interest every 2 months. And that's what we'll work with. Then the number of compounding periods in 24 months, well, it's every 2 months to be compound, so it would be 12 compounding periods. And then we can plug that into our formula, the alternate formula I gave you on the other page. So it will be 1 plus I to the S, and that is just 1,000 times 1.01 to the power 12, and of course you need to use a calculator there. So I have 1,000 times this number here raised to the 12th power, and that's approximately $1,126.83. I have a second example. In this case, we'll use the initial formula I gave you, this one up here. So we have a Ms. Ortega who deposits $10,000 into a bank account that advertises a 2% nominal and annual interest rate, which is computed monthly. Assuming no withdrawals have been made, how much is the account worth after 3 years and 6 months? Okay, so we have the formula. It's just a matter of identifying what to plug in here. So P is pretty easy. That's the $10,000. R is the nominal annual interest rate, so it's 0.02. Put that in here. Then per annual, there's 12 compounding, so N is 12. And then the length of the time that the money is left in the bank is 3 years and 6 months, but we need to convert that to years. So it would be 3.5 years. And so T is 3.5. And then we have T times N. So 12 times 3.5, that's 42. And then you just do the division, and again, you would use a calculator to raise this number to the 42nd power. And your final answer is $10,724.46. So as we saw, when you compound interest, you get a little bit more money with the same nominal interest rate for your savings. But you may think that if you make that compounding interval shorter and shorter, that perhaps the amount of money you make is infinite. But it turns out that's not the case. It actually it levels off to a limit. So this involves a little bit of calculus, but the final result is easy enough to understand. So bear with me on this. So in terms of calculus, we want to determine, let me point here, we want to determine the limit as n goes to infinity. In other words, as n becomes very large, what does this equal? What does this expression equal for our accumulated interest? Where R is the nominal annual interest rate. Doesn't have to be annual, but let's just say annual. Compounded n times per year, where n approaches infinity, and T is the duration of interest accumulation in years. To this end, we let x equal n divided by r, and then we substitute into here. So we start with this, and then if x is n divided by r, then this is 1 over x. Then you have n equals r times x. So I plug that in here. And then you can just write it this way here. We have this expression to the x and then the whole thing to the RT power. And the trick is, from calculus, the limit here as x approaches infinity, which I've shown here, this actually approaches a number, it's E. It's well known in mathematics. It's called Euler's number. It's a transcendental number, so this is just an approximate value for it, 2.71828. And so this whole expression here approaches P e to the RT. And I've seen this advertised occasionally on bank interest, where they'll say compounded continuously. If we look at the example from Ms. Ortega, and we assume the same interest rate in the same time period, and we plug that into the formula, so 10,000 E 0.02 for R, then times 3.5, we get 10,725.08. So it's a little bit less than $1 more than what you would get doing the compounding from the previous slide. So it's pretty close. As n gets large, as you have a lot of compoundings, you actually get very close to this continuous interest rate. And it's actually easier to compute. You just have P, E, and R to the T to the RT power. So now we've covered three different types of interest rates, and I want to talk next about effective interest rate. For the remainder of this lesson, I want to talk about effective rate of interest. I have a couple of definitions here. As defined by Brown and Kopp in their book Financial Mathematics, Theory and Practice. I referenced this in the overview to the playlist if you're interested in this book. They say the effective rate of interest is the amount of money the 1 unit of capital invested at the beginning of a period will earn during the period where interest is paid at the end of the period. Then we have another definition from Wikipedia. It says the effective interest rate, EIR, that's the abbreviation, effective annual interest rate, annual equivalent rate, or simply effective rate, is the interest rate on a loan or financial product restated from the nominal interest rate and expressed as the equivalent interest rate if compound interest were payable annually in arrears. In other words, at the end. So this is more common definition, but I like the definition from Brown and Kopp better because it's not fixated on a year. It doesn't have to be a year. You can look at any period and compute an effective interest rate over that period. And I'll give you a couple examples of this on the next slide. I have an example here, and I'm going to do several variations of it. And the goal in each case is to find the effective interest rate. So we have a Ms. DeMarco. She buys a house as an investment for $200,000 and sells the house 18 months later, assuming no capital investment in the house, for a total of $275,000. In that case, the gain is $75,000 over 18 months. What is the percentage gain? So in other words, what percentage, we'll call it X, of 200,000 equals 75,000? We can write this as an equation. X over 100, so in other words, what percentage of 200,000 equals 75,000? So if we multiply by 100 and divide by 200,000 to isolate the X, we'll get 0.375 or 37.5% over 1.5 years. And if you want to reduce it to an annual rate, we can just divide this by 1.5 and we get 25%, assuming simple interest. So this would be the effective interest rate per year, and the effective interest rate over the time of the Ms. DeMarco held the house, it would be 37.5%. So you could refer to either one of these as an effective interest rate. It's just they're over different time intervals. Then we can do a slight variation. Let's say she held the house for 30 months and she sold it again for the same amount. Then it would just be the 37.5, but we would divide by 2.5 years, and we would get 15% on an annual basis. Okay, then we have one final variation on this. So again, let's assume Ms. DeMarco sells the house for a gain, and she sells it at $275,000, but she put $25,000 in capital improvements, and she also rented it out, and she got $20,000 for renting, and she held it for 2.5 years. So in that case, the net capital gain would be $70,000. We would put that into this equation here, and then solve for X. That's what I have here. I kind of bundled it all together. So in that case, we would get 35 rather than 37.5 as we got here. And then we would divide by 2.5 and get 14%. So the yearly effective interest rate in this case here, given all these things happening, the house appreciating but spending money on capital improvements and getting some money back in terms of renting, the effective interest rate is less than in this case here. In general, if the value of an investment is V of t at time t and V of t hat at some later time, t sub t hat, then the effective interest rate from the first time to the second time is given by this formula. So if you recall from our example in the previous slide, we had a house that was purchased for $200,000 and then it was sold for $275,000. So that would be the difference here, and then we're dividing by the initial cost, so that would be 200,000. So you're dividing 200,000 into 75,000, and that gives you a decimal. And if you want a percentage, then you would multiply by 100. I left the 100 out here. It's just that, so you're just going to get like we had in the previous slide, 0.375. So in words, the effective interest rate formula indicates the increase or decrease as a fraction of an investment from time t to a later time t hat. So it could be negative. I mean, you could, our example, the house appreciated, but you could have lost money, and then you would have a negative value here, which would basically indicate a decrease in terms of your effective interest rate. So we can compute this for specific types of interest rates. I did it for the compound and simple. So here you have, and this is between two time intervals, so time n minus 1 and time n. So this is how much money you would have made on your principal at the end of interval n minus 1, and then this is how much you would have made by the next interval, and then you divide by the starting amount here, and the p's cancel out. The 1 plus I to the n minus 1 cancels with this as 1, and when you divide it into here, you just get 1 plus I. So you have this here, and you subtract the 1 and divide by 1, and just get the interest rate. We can do the same calculation for simple interest. This is the amount of money you would make after time n minus 1. There isn't any compounding, but I guess you could still talk about different time intervals. And then this is at time n, and then you divide by the initial, or not the initial, but the amount after time n minus 1. So the p's all cancel out, and you get 1 plus n minus 1 I in the denominator. On the top, after the p's cancel out, you notice the 1's cancel, the n times I cancels, and you just get a 1 here times I. So you get this formula here. So the effective interest rate for compound interest remains constant over time. It's I. And again, this is just over an interval from n minus 1 to n. However, the effective interest rate for simple interest decreases over time. As n gets larger, so this gets smaller and smaller, because the reason for that is there's no compounding. You may see at banks the annual percentage yield being advertised. They'll say something like 6% interest compounded daily with an APY of 6.183. And the way they compute it is using the effective interest rate formula we talked about on the previous slide. They just put in how much money you would make compounding daily in this case. This would be your end point, and this would be your starting point, P. And you divide by that, and you cancel the P's out, and you just get this result here. So for the 6% compounded daily, N would be 365, and 6% is 0.06 in terms of the rate, and you subtract 1, and you get 0.06183 approximately. And if you multiply by 100, you get the interest rate, the APY. Okay, and you can also work backwards and solve for r in this equation. You add 1 to the y, then you take both sides to the power 1 over n, then you subtract 1 and multiply by n. If you didn't follow, that's okay. I'm just talking you through it if you're familiar with doing that type of algebra, but here's the final result. So if you were looking for the r in this formula, it's given by this here, and I can give you an example. What nominal interest rate compounded monthly now is equivalent to an APY of 8%. So now n is 12, y is 0.08, y in this formula here, and what we want to find is what was the rate, rate that's being compounded monthly. So we plug that into this formula, and we see that if you had a rate of 7.7206 approximately compounded monthly, then over the course of a year that would be effectively 8%. So I also have a Python program that does some of the calculations here, and I'll explain how to use that on the next slide. And that'll be the last part of our lesson on interest rates. Then I have a part 2 on interest rates that'll cover some more advanced topics. I'm showing here the graphical user interface for a relatively simple Python program I wrote related to our work on interest rates. And I'll show you how to use it here. So you put in your initial principal. Let's just try something easy, $1,000. And then you pick what type of interest you want to do. Let's do simple. And let's say it's 7%. So that would be annual. And then you would say how long. So let's say it's 2 years. And then we can hit the compute button here. So you can see that we got $70 each year, no compounding. So as you would expect, it's 1,000 plus 140. So in other words, $1,140. We can clear this. We can use a different number, say 5,000. Let's say it's 10%, compound it, and let's say it's 365, and let's do it just for a year. Okay, so we got 5,500, 25, 78. What would be interesting is to put in the same numbers and see how close it is to this when we do continuous. So let's do that. So put in 5,000, 10%, and we'll do it for 1 year. Okay, so almost the same, which is, if you recall from my lecture on this topic, when n is large, in other words, the number of compounding periods is large, which it is here, 365 for the compounding interest, it comes very close to continuous interest. So we've kind of shown that. Okay, so you can do any one of these three. You want to play around with it, you're welcome to it. I'll give you the link. It's basically in the same file I mentioned on the previous lesson that had the arithmetic and geometric progressions. This file has got a different name, interest, and you're welcome to download that and fool around with it a little bit. And by the way, I wrote this a few years ago manually, and I put it under Claude AI, and I asked it to see if there were any bugs, and it found a few places where there could be problems, and it also created this, it added simple interest to it, to the graphical user interface. So that was pretty impressive. It understood what the program did, and it was able to check for errors and then also add something to it.